Okay, so uh, this is lecture 16. So last class we talked about the 3AP problem and kind of this. I'd say maybe the main takeaway should be this what I'm going to call structure versus randomness 2.0, in the sense that we are still looking for some kind of dichotomy or win-win analysis, but we're looking to exploit some operations, right? Meaning something like spreadness implies mixing. Convolution, matrix products, they can amplify the randomness that you have, and we were exploiting that, okay? So today we are going to, maybe switch gears a little bit and talk about two problems in computer science, and in the sense that they're more about data structures, algorithms, and so on, okay? And we also briefly discussed how it connects to communication complexity last time. Graph algorithms as well. So today the goal is we will go back to kind of using polynomials. And the way we're going to use them today is to encode computation as polynomials. This is an old idea, arithmetization it's called. And it has led to many important results in computer science going back to the 80s, 90s. It's very important in cryptography and so on. Today we're going to look at it from the perspective of designing space optimal algorithms. And for one particular problem specifically, which is the tree evaluation problem. Okay, so this is a recent result which has had some other uh, very interesting follow-up works based on this. But before starting tree evaluation problem, I'll describe what the problem is, what the result is, and then we'll go back all the way to the 80s and 90s and talk about a beautiful sort of almost like 10-line algorithm by Benor and Cleve on evaluating arithmetic formulae. Okay. And if you know complexity classes, this is basically another way of proving Barrington's theorem. But if you don't know what they are, then that's totally fine. There's this complexity class called NC1, and it shows some kind of upper bound on what NC1 can compute. Okay. But the problem itself you can understand from first principles, so that's what we'll do. And just as announcements, exam 2 grades will be out tomorrow. Okay. And yeah, and exam 3 is the week after, I think. So for exam 3, let me just take a straw poll here. Would you like me to go with the university schedule? It's a take-home exam, so we can adjust it if you want. Would you like to keep with the university schedule in the finals week, or maybe go a little ahead? What do you think? How many people want to go like maybe this Thursday to Saturday? 3 days from now, or like the actual university schedule. In the past, I've seen people say that they don't want it to overlap with the finals because take-home exam, if they have other exams, then yeah. See, one person who wants to go earlier. Let's say how many people want to go earlier? Yeah. It'll be 2 days again because it's not. If I give it the whole week, it'll still be the last 2 days. I know. And I don't think it's worth giving the whole week because it disrupts the schedule for all of the other exams for many people. So just the 2 days and about 8 hours of work or something, right? So yeah. What's the university schedule? Yeah, Monday evening to Wednesday evening. As I said, it's a take-home exam, so we have the flexibility to adjust. But the biggest adjustment would, I don't think it matters that much when you go during the week. But in the past, people have asked for it before, that's fine. So if you want, we can do Friday to Sunday, or I don't know, I don't like spoiling people's weekends, but if you want Monday to Wednesday. So there are 4 people who wanted to go early. So it seems like majority still wants to go with the current schedule. Okay. We'll stick to that then. All right. So let me start by describing the problem. And so the problem is going to be what's called tree evaluation, right? So it's a very good name. The entire problem is in the name. So okay. So what we have is a tree which is encoding some computation that we have to do. Okay. Usually, when we think of arithmetic circuits or arithmetic formula, you might think of like a tree where you have, maybe AND gates, OR gates, and stuff like that. Okay, something like this, right? So on, and then maybe you'll have the variables at the leaves. Okay, and if you have such a thing, you can imagine how the computation is to proceed, right? Any such diagram, any such tree encodes a function, right? That has to be computed. Given these inputs x1 through xn, you can propagate the values up the tree. Okay. And today we're going to look at a slightly more complicated version of this setup, where the gates are kind of themselves somewhat complicated. Okay. So each of these AND or OR gates will now be replaced with some other function. Okay. All right. So what's the setup? So imagine, again, you can think of more general setups, but let's think of the basic setup, and then we'll see what we can say about it. Have some function f. Think of it as like a basic gate, right? And instead of just taking 2 bits at each of our gates, we're going to take 2 bit strings, right? Or in other words, our alphabet is not just 0 or 1, it's something slightly bigger. Okay. So each function is going to take 2 strings, or in fact, we'll only have 1 function, and the output is itself k-bit string, right? You can imagine putting different parameters, but as I said, let's standardize everything, simplify everything so that we get to the main essence of the ideas, right? So I have this function f, okay, that's it. And the tree is also the very simple, complete binary tree, okay? So what do I have now? So I have something like this. I'll draw it for maybe uh, okay. And so each of these leaves, you can imagine, has a variable or a constant. Let's just have variables in there, because you can even put in constants just as variables if you want. All right. So the height of this tree is 1, 2, 3. And the number of variables as n is 2 to the h. Okay. And how does the computation proceed? And each xi is not a bit, it's a k-bit string. It's really a chunk of k-bits. Okay. And now how does the computation proceed? You would compute f of x1, x2 here, right? And this would compute f of x3, x4. Okay. And these are once again k-bit strings, so you can just propagate all the way up. All right. So in some sense, if I call this a node u, and this left child as left and right child as right, then the main sort of recursion that we're looking for is, u dot value is supposed to be f of okay, you compute whatever the left subtree is computing, whatever the right subtree is computing, and then you evaluate f on it, and that's the associated value. Okay, very simple function. All right. So what's mysterious about this? What's there to be solved about this? What's the question here? Just imagine someone gave you this tree in terms of some data structure, right? So you can query, as I said, the tree is also very fixed for us. So let's just assume the tree is like, given the root, I can always go to the left child, right child, left child, right child, left child, right child. I can parse it in any way I want. Okay. And you have access to the input. I can always query, okay, tell me the ith bit, tell me the 10th bit, tell me 17th bit, and so on. Okay. And the goal is compute root dot value. And you also have some kind of, let's say, the exact model for how you can compute f is not that important. But let's say for now that you can even give any inputs and then query, and then you'll immediately get the answer for f. Okay, it's not going to be exactly unit cost. That's important. But let's assume it's almost like unit cost. Does the problem make sense? We have this tree. We're trying to compute it. Now, how can I compute it? Okay, let me just ask that. It almost sounds like computer science 101. How do I compute something like a tree value? Just tell me, yeah? Recursively, right? So how would you say? You'll say something like evaluate node if node equals leaf. I'm writing it kind of in this more detailed sort of almost like code because it's helpful. Some of the details are very important and they'll play a role. So I'm trying to be as careful as I can. I don't know if I'll be very careful, but hopefully it'll be fine. If it's a leaf, I'm just going to return the value. Okay, meaning, when I just look up the corresponding variable or return the constant what is stored in that leaf. Okay. Else, we don't even have to worry about any border cases. It's a completely balanced tree. So you'll just say, okay, that's it. So I evaluate node dot left, evaluate node dot right, and then I'm done. Okay. So it's very efficient. It's linear time in the sense that you're basically, maybe if there are n nodes, you'll take 2n times, the time for evaluating f. So it's very efficient time-wise. You have to access everything. Maybe within a factor of 2, you're almost there. But how about space? So whenever we think of evaluation and efficiency, there can be different resources that are important. In terms of time, this code is almost as good as we can get. But how about space? How much space would this need? Any guesses? Yeah. Maybe 2 to the edge. N is 2 to the edge, right? Yeah. So, okay. So question. How much space? And the first answer was, maybe roughly N. And any other guesses? I would say your answer is correct under most implementations. Okay. So one of the sort of the third rail of programming is when you do recursion, you have to keep their memory separate, right? Otherwise, who knows what happens? Okay, you want to allocate each one its own thing. Do not touch what's happening inside. We want to keep things modular. Okay, if you do that, then essentially what we're saying is, okay, this call is going to use some memory, but that has to be separate from what I use here, and so on. Okay, yeah. Yeah, one after the other. We could, but standard implementations, it's not clear they would, right? They would just say, okay, do this, and then you have to release that memory and then do something. Okay, so that's where I'm going next, right? So if I just do it naively, maybe you would assume each time I'm using separate memories for left and right, but that's a little bit redundant, right? Yeah, you have. Yes, exactly. Well, almost. Okay, so can you make it better? I think the guess was height of the tree. Okay, and we can, with a small caveat for the height of the tree. Okay, so as I said, I'm going to write this again in a bit more gory detail than is needed, but it's helpful, right? So just imagine that my memory is split into registers or blocks. Okay, so each RI here is a register, and just imagine it holds k bits. That's a unit in some sense, okay? Because that's like, 1x1, x2, or something like that, right? So ideally, you would reuse stuff, okay? So how can I potentially reuse it? Yeah, okay, maybe for this, I don't have to be that careful. So let me call this tree eval, okay, of, let's say, u, and yeah, that's it, okay? So what we're going to do is somehow I'm going to write it carefully because we want to reuse the memory from the left call for the right call, but we don't want to overwrite everything, right? We have to store at least the answer that you got, and then you can reuse everything, okay? So this, just to normalize and set up some sort of standardization, I will say first, the output will be stored in RD, where D equals depth of U, depth or height of U, okay? Or maybe I should say height. That's important. Meaning, yeah? Yeah, yeah. Just again, you can do either way. I just had to fix something so that I'm consistent, okay? So I'm going to fix it like this. So the idea is that every time you make a recursive call, I'm going to reuse the memory, but I'll keep one extra register to store the answer. Okay. So what does this mean? Now you say if first compute, d equals height of U. It could just be an attribute of the tree, or I can just compute it again. It doesn't matter. And then you say if u is a leaf, let's just set R1 equals u dot value. Return. Okay. And otherwise, what do? I would say first t eval u dot left. Okay, I call the evaluation function u dot left. Now the height of the left tree will be 1 lower. Right? So its answer is going to be an RD minus 1. So what should I do now? If I call u right, it's going to be overwritten potential. So I have to store this RD minus 1. Okay. So I would say RD, I'm going to copy it. And then do the same thing. T eval u dot right. Okay, and then set RD equals f of RD minus 1. Right? So this computed the left thing, but I'm storing it with one extra register. And then do this. Okay, very simple. Any questions about this? Okay, so what did we get here? So this runs in space, which is basically theta of h times k. All right, because if you have k bits, each register has to store k bits, and there are h things in total. So I have to allocate this R1 through RH and store them. And there's no kind of nice way around it. The time is linear. Okay, and here's the main thing. In some settings, k could be big. Okay, and the most interesting setting is the case where imagine k equals h. It's basically log n. So each node stores log n. That's like the word size. And I have n things. And if I do this thing, the memory is going to be the memory usage of t eval k comma h, we know is theta of kh, which is in this case log square. Okay. And there was a long-standing conjecture that you couldn't do this better than log square. Somehow it seems like there's really not much you can do here other than this simple recursive thing to save space. Because how can you do the recursion without even storing the left value? Right? If you don't store the left value, what's the point of computing it? And if I store it, I cannot overwrite it when I go to the right call. So every recursive call seems like you need some extra memory. Okay. And there were some improvements until minor improvements and so on. But last year, there's this beautiful result due to Cook and Mertz. They gave a new algorithm, and we can compute t eval in space. K plus h is the bare minimum. I have height h, and k, so it's saying k plus h log k. Actually, k plus h is not clear as a minimum, but the k is at least the minimum, and this is in k plus h log k, I can do it. Okay. So in particular, for example, if k equals h equals log n, then the space is O of log n times log n. Right? So I'm getting quadratic improvements on the space. Okay. Any questions about this statement? And this should be surprising. it was surprising to many people. Not often do you get like algorithms that go against what we expect, and this is one of those cases, right? And today, and maybe a little bit of the next lecture, we will see the full proof of this. It's for such a result, you don't need very heavy machinery or something. It's almost like a some clever tools put together. The code itself is maybe like 20, 30 lines. Okay. And following this, seems like okay, maybe it's a curiosity. Why do you care about tree evaluation so much? There are many reasons. First, tree evaluation shows up implicitly in many other problems. Like there's something called KRW conjecture, data structures, and so on. Perhaps the most striking example of this that only came about like maybe last week or so was is this new result by Ryan Williams. It's going to appear in conference in July. He used Cook-Mertz's result in some souped-up way, along with some clever tricks to show that, again, I'm not going to specify the full statement. You need some constraints and T and so on. Take any Turing machine, any algorithm which runs on multi-tape Turing machines with time T of n. Okay, basically think of it as an algorithm which is running in time T of n. Because we want to be very precise about the parameters up to some, even quadratic and so on. So we have to fix a model, and the model is multi-tape Turing machines. Okay. So multi-tape Turing machines. So any function that can be computed by a multi-tape Turing machine in time T of n can be simulated in space square root T of n times some polylog things. Maybe it might have been even 1 log. Okay. It's saying I can always, if I just say I have time T, the only bound usually I get on space is T, right? Because each step I can access one extra memory location, and many algorithms do that. Even if I'm just writing down everything, once on the tape, it might take time T, space T. Okay? And what this simulation result is saying is that any algorithm which runs in time T can be simulated in space square root. And this was very surprising. It is very surprising to many people, definitely for me. I did not expect that you could get universal savings on time when you go to space. Okay. And the way this is done is basically kind of, it exploits this sort of, we are getting this quadratic savings in the space. Okay. And there's some clever reduction to convert a multi-tape Turing machine to some kind of tree evaluation problem, and then use this Cook-Mertz simulation more or less in a black box, okay, with some slight extension. All right. I don't think we'll have time for the second one, but at least for the first one, we can do it in detail. All right. Okay. Any questions about kind of the big picture, the questions that we're going to address? All right. So before going to all of this, I want to, as I said, go all the way back to the 90s and talk about another result which has the same flavor, and the algorithm that we're going to see for tree eval will look much less magical once we see this. Okay? And so put the tree evaluation problem on the back burner for now. We'll talk about another tree evaluation kind of question, but in a much simpler setup. And this I'll call Benner and Cleve formula evaluation. Okay. So before starting tree evaluation, let's think of a simpler task, which is formula evaluation. Okay. Usually when we think of formulas, again, we think of Boolean and or and so on, but let's think of arithmetic formulas. So meaning something like, I can use variables, I can use constants. Let me use both. I'll give some examples of both. So let's say my formula is something like this, right? I give you this. I'm sure everyone can answer this in a second or two, but that's not our goal. Let's think how a computer would evaluate. Okay. If I give such a formula, what would you first do? What does an algorithm do? How do formula evaluators actually work? They make it into some kind of tree by postfix, infix, and so on, and then you evaluate. Okay. So let's say, I convert it to tree again. So what would the tree be? Okay. So implicitly, it's kind of the same tree evaluation problem, right? I have a tree. Depending on the expression, it might not be balanced, but at least every node has 2 leaves. If it is not a leaf already, and so on. Okay, let's say we don't have any unary operations. You can have negative signs, but let's say we put them on here, and so on. Okay. And if I give you such a tree for a formula, again, imagine a huge formula, right? With n nodes in it somewhere, depth h or height h, how would you evaluate? I'll do the same recursion, right? In some sense, that seems to be the only arrow in our quiver, so I can just use recursion again. Okay. So let me just copy that. And I'm putting down small numbers here, but they need not be small numbers, right? They could be whatever numbers that your arithmetic, allows. Okay. So let me call this formula eval. Okay. And I should really use the same concept of registers. Right? If I just call on the left, I get an answer. I need to store that answer before calling the right, because I have to do this operation again. Right? Okay. So it's almost the same thing, maybe just a little bit more cases. Otherwise, you say if so f eval u dot left. Okay. And then you have a little bit of cases in that you would say if the operation is plus, you set RD to be RD plus RD minus 1. If op equals star, RD equals RD star. Okay, simple enough, right? So the number of registers or word space I would need, the memory is basically going to be the height of the tree. Okay, each word now is just a number, which we'll think of as a constant for now. So it's mainly about how many numbers do you need to really store. Okay, so this is space h. Okay, or h numbers or words. Any questions about this? Okay, but this is not the best we can do. In 1989, Barrington showed that I can actually do this with constant number of words. Okay, so just constant number of, if I think of the bit complexity also as small and it's like a Boolean circuit, it's a Boolean formula instead of this thing, he actually showed that you can do it with only the number of states is 5, not even like bits, but number of states is 5. Okay. But what I want to show today is this very beautiful, clever algorithm. So this Barrington's result used some, it was also simple. It used something about solvable groups and so on, which is kind of surprising. But the Benor and Cleve, I think, is more intuitive. So Benor and Cleve, I think it was 90. What they showed is that can compute f eval with 3 registers. 3 registers. That's it. It doesn't have to grow with the height. It's only 3. It almost sounds like the bare minimum, right? So I'm basically saying I'm going to use something for the left, something for the right, and something for the answer. That's it. And I don't have to, I can reuse stuff however which way I want. Okay? So how do we do this thing? First, let's slightly abstract out what it means to have a program with only 3 registers. Okay? And this leads to this definition of what I call, what are called straight line programs. Okay. So straight line programs just mean you have a set of instructions that you want to follow. I have some registers like R1, R2 up to RL, and you are just writing down instructions like set R3 to be R1 plus R2. Maybe R4 is R1 plus X2 times R10 and so on. Okay. So straight line program just means that each line involves at most 3 registers. One that you're using for assigning. On the other side, you might use at most 2 other registers and some input values. Okay, very simple instructions. Okay. We are going to specialize to this because it helps narrow the space. And in some sense, if you look at our program here, this is a straight line program, right? So every instruction that we do in the end is just involving 3 things. Either like a, value, just like a straight up assignment here, or some equation like this. Okay. Any questions about this? So that's what a straight line program is. So let's see an example of how to do this. It was a bit painful, but I could get cursor to, I wrote up the Benor and Cleve thing and then use cursor to help get the formatting and so on. When I asked it to do it directly, it struggled a lot because there's some cleverness in this 10 lines and, oh wow, the color is so terrible. This is bizarre. Okay, anyway. I need to go to Zoom because I need to share. Okay, so let's see. So this is actually Benor and Cleve's thing. So this is my formula, something like, okay, it's harder to draw them as we are drawing on the ASCII. So this is the tree. Start with 4 and 5 plus, and then 3, and then 2 at the very top. That's the expression. Okay. But now when I ask it to generate the program, it generates a sequence of instructions for this. These are all the instructions. Okay. And there are only 3 registers. That's the point. Benor and Cleve thing says that I can evaluate any such thing with only 3 registers. So the height of this tree is 1, 2, 3, 4, So you will probably need 5 things here, and now we're only using 3. And of course, you can go, no matter what the height, you'll only use 3 registers. Okay? And the answer is correct. You can do all of this. It kind of seems very weird, right? That you're only using 3 registers, things are going all around, but you end up with only 6, the right answer. Okay? You can try something else. Maybe let's make it a little more complicated. Okay, so this is the tree now. The height has increased. The number of registers used is still 3. And you also notice something strange. These numbers are, the final answer is 3,430, but intermediate ones are going higher. Okay, so this plays a role. We're going to do subtractions and so on to save on the space. Okay, and as I said, we're doing with numbers, but if you're doing with bits, there's again a nicer way to do this where none of these go to other values other than bits. Okay, yeah. Right, so you can easily get that out, but this is kind of the simplest implementation, right? So otherwise, you can do some other tricks to get it out. Okay. Any other questions? If for instance, if I assume the inputs are all bits, I can make sure this is all just bits. So 3 bits. So it's like space 8. Okay. Or number of states is 8. Any questions? We'll see it in action, and I also have a video for that later on. But let's go back to, I just wanted to give you a sense of this being possible. Okay. All right. Okay, so how does this algorithm work? It works based, as I said, we're going to write down the straight line programs. And let's focus on kind of the, so our code is going to be kind of recursive again, right? So we'll focus on one node, more or less. So just imagine I have one node. Let's call this U. This is op. And then I have U dot left, U dot right. And I have 3 registers. Okay. And so the main idea, which is, again, this is a strong sort of the worst possible practice in programming. Every time you take any programming course, they'll say every time you're doing any compiler thing, you should not touch the memory that is inside a subroutine by another subroutine. If you start doing this, things will go haywire, right? But we are going to do that in a very controlled. Okay? What do I mean? So we're going to build some subroutine. The main idea is I'm going to use all 3 registers when I do u.left. Okay, its answer will be stored somewhere. I'm going to do the same thing when I do u.right. Okay, but we're going to do this in a way so that the first evaluation that you did doesn't get destroyed. Okay, another word for this, which kind of makes sense, but I also don't like it, is catalytic computation. If you think of a chemical reaction, you have this catalyst which make the reaction go through, but at the end of the thing, they're supposed to stay as they are. Okay. In the same way, the main idea is use the other registers, but restore. Imagine I have some number of registers. I'm going to use all of the registers I can, put the answer in one. But when I finish the computation, the other registers should be restored to whatever value that they had in the beginning. It almost seems like, too much of an ask. Right? You use them. If you have to restore them, maybe don't you have to store them? Then you probably don't you have to use as much memory? It turns out you don't. You can be clever about it in a way that restoring takes you less space than just starting from scratch. Okay. All right. And the other thing we're going to do is kind of abstract away even more or simplify our design space a little bit more. Straight line program, as I said, the instructions are like, you have 3 registers, one on the right, which is being assigned, and at most 2 others on the left. Okay. Instead of that, we will use something called offset here. And the same will come up even in tree evaluation. All right. So offset is going to take some u, basically some tree, right? U is a node of a tree, so it's the entire tree at some point. And I'm going to take 3 registers. Let me just call them Ri, Rj, Rk. Which is first, which is left, which is right, they'll keep changing, right? We'll keep playing with the ordering of these things in a clever way. So when I call this, what should happen? The answer should be the following: Ri, Rk don't change. Okay, goal. And Rj, what should happen to Rj? It should be offset by the value that we want. So ideally, I want Rj to be the function value associated with u, right? So instead of that, I'm just going to say it's going to be Rj plus the formula at u evaluated on all of the inputs, whatever the actual value is, right? And let me just call it x. It doesn't matter. It's really the value associated with it. And then I have, but I'm also going to call for this. Okay. So this is a basic primitive we're going to target. It's almost like getting the value, but instead of just getting the value associated with u, I want to compute this offset. Obviously, if I can compute fu, then I can get here, but we're going to target this directly. Any questions about the definition? So a recursive thing is going to use this as a subroutine. Instead of evaluating the formula directly, we're going to ask, okay, can I compute this offset? The ordering is important. So the target is the middle one. So we're going to offset the middle one, okay? And the other 2 should not change. But the offset is also depends on this Ri, the first register's value. Yeah? Not Rk. Rk is kind of like the placeholder, right? It's our additional memory that we're going to use to make this computation work, but it has to be restored to its right value. Okay. And if you can do this, that's basically what's going to happen. I'm going to just imagine I call this on the left subtree, but so that the answer is stored in Rk. Then I call the right subtree, but then Rk is there, you can use it, but it has to be restored. So I did not destroy the left's value. And then keep going. Okay. So that's what we want to do. So how do we do this? Actually, 10 lines of code. We'll do it by recursion. And in fact, instead of drawing a big box, there are some easy cases, right? So if u is a leaf, it's easy. We just look up the value and multiply it, right? Actually, let me just do one other thing. We have to slightly, we don't just use addition, we also use subtraction. So let me also put a flag here, which is called sign. Okay, which just means that, if it's 1, I have to compute Rj plus Ri star Fu. If it's a minus, I need to do Rj minus. Okay. So my goal is to compute this guy. Okay. Right. Okay. So now if U is a leaf, it's easy, right? I would just say set Rj is Rj plus sign Ri times U dot value. Okay. And you can think of the program or the entire computation is going in 2 stages. First, I write down all of the instructions for my straight line program, and then I go and evaluate it, right? Which was happening exactly in the code, right? So first I figured out how to write down all of these instructions. I can actually do that also in small space, but that's not important for now. But I write down all of the instructions, and once I have it, doing the evaluation, I only need 3 registers. Okay. It's still kind of very amazing that you can do this with only 3 registers to me. Just imagine a huge formula. How do you do it? With only 3 numbers extra stored, 3 bits extra. Okay. These were all bits. You would only be doing 3 bits extra. Okay. All right. So how do I do this Rj plus sign? Well, if it's a leaf, it's done. On the other hand, it's not a leaf, but let's say U dot op is a plus operation. Meaning, in some sense, multiplication is harder. If it's plus, I want to say it's easy. How can I do it? So what is the goal, right? So we want Rj to become Rj plus Ri times Fu, the function associated with U. Now this is going to be times the function at U dot left plus U dot right. Right? So if I'm trying to compute plus, what should I do? Any guesses? What should I call? The point is addition is just, commutate, you can do it one after the other. Right? So I can just say offset U dot left Ri, Rj, Rk. Okay. And when I do this, I end up with Rj becoming and then just do the same offset. This is what it would do, but with the current state of Rj, which is already, added up, right? So this would mean I get, maybe let me write it properly. So I have left here plus Ri times. Okay. Makes sense? So if it's a plus operation, it's very easy. Because of the way we define offset, offset had multiplication here. So if it is a plus gate, it's very easy. Okay. Any questions? What do you do when it's a product? That's where the real sort of, magic is in some sense. Sorry, not minus, but let's just say star. Okay. I should say, this is all assume sign equals 1. Okay. I'm doing this for +1. If it is a -1, then you just have to have another case where sign goes through. Okay. So you can just put it there, but I'm going to focus on sign equals 1, but the recursion will use both. Any questions? Yes, no? Seems fine? All right. Okay, so now let me talk about the multiplication. So the idea for multiplication is that there is a series of 4 commands that you can write down, which will actually do the multiplication and restore the other values. Okay, it's a very clever, simple program. And let me first write it down. So we have Ri, Rj, Rk, and let's, just for brevity, let f equals the u dot left, g equals u dot right. Okay. So the sequence of updates I'm going to ask for is the following. I'm going to say set Rj to be something like this. So I'm doing a minus times Rk times j for whatever reason. Okay. And then I'm going to say, how did they come with these 4 things? I'm not 100% sure, but they did it. So that's what we're going to go with. Okay. I'll write down these things and then we'll verify. So the third line is we're going to do Rj is okay. So I wrote down 4 instructions for this straight line program. Don't ask me how you came up with it. Maybe they had some nice trial and error to do it, but we'll just check that it works. Okay. So let me write down the states here, right? So the initial values are Ri, Rj, Rk. What does this, here after this update, I'll have the initial, let me put a bar over them just to distinguish the initial from the current things. Okay. The initial things were Ri, Rj, Rk. Now this will be the other 2 did not change. This got updated, right? This is the triple. When I come here, what happens? Ri bar does not change. Rj does not change. Okay. But Rk is becoming okay. And then I have so you take the current Rj, right? And you're offsetting by the current Rk times G. And you can see what happens. The minus Rkg that you did is getting restored when I do this computation, right? So I'm going to multiply this with G and add it into this. So what happens when I do that? I get Rj bar plus Ri bar times F times G. Okay. And then the only thing left to do is to restore this back to its original value. So we got what we wanted. Everything, all of the registers I and k are to the right value, same previous value. The jth thing is offset as we want. Okay. So one thing to keep in mind is that even though this is simple, if you actually think about it, it's kind of complicated recursion, right? So when we think of the tree, we are originally making only 2 recursive calls. Now we are making 4 recursive calls. Okay. And not only that, when I make the recursive call here, I'm changing the role of I, j, and k. So which is target, which is being offset, right? So I need to change the ordering of the registers as well. Okay. So that's the entire algorithm, right? So you just write this down as a sequence of things. Any questions about this? Very clever, but it's simple enough, right? You see it, you can verify it. How you come up with this, I think it requires a lot of trial and error and some intuition that it is possible. Okay. So let me write down the actual code. You would say something like this. When I'm trying to do multiplication, I would do first is okay. So remember, we're trying to do ijk the order, but instead I'm doing kji. All right. And then offset u dot left, ri, rk, rj, comma 1. Okay. So that's it. And if the sign initially was a -1, this would be a 1, -1, -1, 1. Okay. Yeah, these 4 lines are somewhat clever. I gave the pseudocode to all of the LLMs and asked them to implement. They all struggle massively. Okay, but it's just 4 lines, but you can just, the ordering is a little bit tricky, but you can do it manually easily. All right. And that's it. That's how you compute the thing with only 3 registers. All right. So maybe let me show it to you once again. Okay, so this is, oh, it's too small, but never mind. You can see these are the 4 lines, right? The exact same things that we were talking about. Okay, and where did my terminal go? And the instructions are exactly like that. Once you get to the leaf, you get the constants. Otherwise, you write down all of these things, which are the function values. And you can see there's some pattern to the minuses and pluses because that's how everything is going. So you put 1 minus and 2 pluses and a minus to restore the values, right? Okay. And after I got the code to work myself with some bit of pain, I had it converted into a Manim video. Does anyone know what Manim is? 3 blue, 1 brown math animation. So we can take some pleasure in viewing this. So this is the formula tree. Those are the read registers. So the legend is supposed to explain. The colors are terrible here, but basically the colors are showing which ones are going to be offset, okay? And which ones are kind of, the roles will change. Maybe it's yeah. The 4-step process, let's use the visualization with the expression 2 times 3 times 6. So you're evaluating this subtree here. So that got updated. And then you go restore the other stuff. Wait, what happened? Did I do a mistake? No, it's fine. It's fine. Yeah. You can see every register changes its value at some point or the other. And eventually you'll get to the right answer. Okay. And just a couple more minutes. So it also says, all 3 registers roles change during recursion. So that's why you need 3. Otherwise you would only need 2. But every register changes its value. And here actually R1 never changes. Basically, when you have nested multiplications, that's when the roles really change. Plus, you're not changing the order of the registers. Okay. In fact, if you have just only pluses, you can just do it with 1 register. You just add up one after the other. You don't have to reuse the space in any way. It's the mix of the 2 which makes it more powerful, and that's really important. Okay, this is a much messier example. And so it's evaluating this subtree here. That's the recursive call it's on. It did it. It restored the values, and now it moves up, and so on. Maybe I can speed it up now. We should increase the font size for the middle. Okay, that's it. So 318 is the final answer for that. Okay. All right. So that's for the Benor and Cleve algorithm. Now, as I said, it's a kind of a cool result that you can evaluate any arithmetic formula with only so many things. Right. And as I said, it also has a very important complexity implication, the same thing, that NC1, which is a class of all circuits, all functions which have log depth arithmetic formulas, can be computed by constant width branching programs or straight line programs. Okay. If you don't know what those terms mean, that's okay. It's not important. But let's see how the same techniques, same kind of ideas underlie what's going to happen for the tree evaluation, right? We'll play the same tricks. Somehow I'll keep some registers, I'll reuse the space and restore the values using something like this offsets again. Okay. But we'll have to pull out polynomials from somewhere, and they'll come in as we'll see. Okay. So let's take a short 5-minute break, and when we come back, we will revert back to the tree evaluation problem. Okay, so now let's go back to this Cook-Merckx statement that you can do tree evaluation with space almost linear, like we're saying quadratically in the dependence on K and H. So just to recall, we have this fixed function f, 0, 1 through the k bits, 0, 1 through the k bits, and it's outputting 0, 1 through the k. Okay. And what we're going to show is kind of along the lines of what what we just saw in for simulating arithmetic formulas. I can do this with 3 registers once again. Okay. Now each register, instead of storing a number, is kind of going to store k bits, right? So earlier, we had to have height of the 3 many registers. Now we'll only have 3 registers. Okay. So I'll first give kind of high level overview. So we'll have 3 registers. Okay. And think of them as k elements long each. Or in fact, when I say, maybe let me not say 3 registers. We're going to use 3 times k many registers, but imagine the registers are kind of grouped into 3 groups. Okay. And the reason I want to view it this way is we're not going to work over 0, 1, even though my function really is only on 0, 1, right? 0, 1 bits. And then the tree evaluation function itself is something which takes input 2 to the h and gives out 0, 1 to the k, right? So this is all possible leaves, you're giving values to them, and I need to get a k bit output. Okay. But we're going to extend the domain in some way, right? How are we going to extend it? I want to pick some field, finite field f, okay, of size m plus 1. Okay, we'll pick a field, some finite field of size m plus 1. There's some, something you have to check that I can do this finite field operations also in small space and so on. Those are much more standard, so we're not going to belabor that. Let's just imagine that field arithmetic is free. Okay. And each of these 3 groups of registers themselves will hold k registers, each one holding a field element. Okay. So this is going to be a field element, and so on. Okay. All right. So concretely, we have 3k registers, each holding a field. Okay. And this goes back to the question that you're asking earlier about, would the numbers blow up if I keep doing this and then bring them down, right? Using finite fields is a way to prevent that. You can even work with reals, but you just don't want things to blow up too much. You do finite fields, so the numbers are always like, in the same range. Okay. Now we're going to target getting the same kind of register programs. So what does register programs mean? Right? So just as before, I want to say something like offset a node u, and let me use RA, RB, RC, and assign just as before, right? And the result should be It's very similar in that we are looking for an offset, but this time there's no multiplication with the first register. I just want to offset with the function value. Okay. The reason is the function itself is going to be complicated, so we have to do more in the function space rather than multiplying with Ri and so on. Okay. Similar structure. And let me introduce some notation because it's quite helpful to have it. So we have these 3 registers. They're all the same size, of course, right? And let me call this RA1, RA2, RAK. This is RB1 up to RBK, RC1, RCK. Okay. And the group I'll call RA bar. This is RB bar. This is RC bar. Okay. And you should think of this bar notation as just something, it's like a vector of field values. When you write it up, you basically write down for loops, but I'll simplify the notation so we can focus on the important stuff. So just keep this notation in mind. Okay. So that's what this bar notation means really, right? I'm adding the whole vectors. So RC bar is going to change where every coordinate, every one of these individual registers is going to change. Remember, F itself outputs K bits, right? So all of these things you have to change a column. Okay. The plus is vector addition. All right. Okay. So and we'll use recursion as before. So let's try what happens if I use recursion. If you a leaf, easy. Okay. The leaf case is trivial. There's nothing much to do. All right. But what do we do otherwise? And here's where sort of the first rabbit out of the hat comes in. We already went to finite fields, and the reason we are doing that is, we have a function defined only on bits, this f, right? But now I increase the domain to some finite field. But I haven't defined what this function would do on other values, right? I want to define something even when it applies on these register values. Okay, how do I do that? Any guesses? I have a function which is defined on the hypercube, but I want to now extend its definition to a bigger space, to some other finite field, like let's say 0, 1, 2, 0, 1, 2, 3, 4, 5, and so on, over some finite field. How can I do that? Any guesses? Make it a polynomial. Okay, so that's the first thing that we're going to do, is look at what are called multilinear extensions. Okay, so given my function f, I'm going to define a new thing, which is I'm going to call f tilde, right? And it's going to take field elements, output k field elements, and with the property that we'll definitely have an explicit value. If my inputs are just 0, 1, then it matches exactly what happens on f, the actual function that we're supposed to be using, right? On the other values, we have the flexibility of defining it, But there is, in some sense, a canonical definition, and that's what we're going to use. The canonical definition is to write it as a polynomial and then just use that extension. So let me just treat it as a claim. We'll worry about that claim later. So let me call it the multilinear extension. There exists a degree 2k polynomial f tilde from okay. So when I say degree 2k, I should really say 2k polynomials. Okay, meaning for every I, there is a degree 2k polynomial which takes and gives a single field element, right? And which is supposed to be the ith coordinate, right? Such that f tilde I of y comma z equals the ith coordinate of f. Okay. In some sense, we are introducing some redundancy in the computation. Like this is what error correcting codes do. So we're going to use some redundancy so that every time when we compute, we're going to compute more information than what is needed. But then when you amortize it, that more information is going to be very helpful. Okay. Not only am I going to compute just on the Boolean things, I'm also going to give you the power to compute it on some other field elements as well. Okay. All right. Any questions so far? All right. So now what do we do? So let me draw this picture again. Just imagine I'm in one particular step of the recursion, right? And when I'm doing this recursion, I'm going to focus on computing every bit, every coordinate of this block at a time. Okay. So meaning, so let's say my goal is to implement offset u and RA bar, RB bar, RC bar, comma 1. Right? So what does this mean? I need my let's say this is my ith coordinate. Okay. So I want somehow to update RCI to be okay, this is what I want to really do, right? Oh, sorry, I wrote it wrong. Let me write that. So this is what I really want to do, and but this is kind of but I don't know where this fu is. This function value, I don't have it in hand. I have to compute it recursively. Okay. And because of the way the current thing is going, let's say I call it recursively to update RA bar. Okay. If I try to do it, what happens? I can potentially make it so that maybe I can make this to be RA bar plus Okay. I call the offset recursively on the rest. The other two did not change, but this changed to whatever it is plus fu dot. Okay, I added something. I call it again here. I get RB bar plus okay. Now, if we did not have these two, our goal would be easy, right? I would just say evaluate f on these two things, you're done. But we have these offsets, okay? And the reason we cannot get rid of them is because if we get rid of them, we won't be able to restore them. That's the whole problem. I can subtract these things out and then evaluate it. But then if I evaluate it and I subtracted this out, I lost this information. How do I restore it? Okay. So that's the whole sort of chicken and egg problem. Okay. But this much I can do, without any loss, with the exact same memory that I have, I can definitely implement this. Let me call this y. Let me call this z. All right. And what else can I do? So from these two things, we can reformulate our goal as so I really want to compute f tilde I of y comma z, but I have this strange offset sitting there. Okay. The only thing that I know is that this f tilde is a degree 2k polynomial. Right? So how can I do this? Somehow get rid of this RA bar and RB bar and compute just the polynomial on the offsets. Okay. And the biggest trick in the book when you're dealing with polynomials is that there is a lot of sort of redundancy in polynomials. Okay. In particular, we have polynomial interpolation. If I give you the value of polynomial at many, many places, I can use this to compute the value of the polynomial at any other point. If you give me the value of the polynomial at enough places, from those things, I can compute it at any other point. All right. So let me rephrase this a little bit, add one more step in between. I can always make a recursive call to compute RA bar plus FU left. I can always make a recursive call to compute this. No change so far. This is something I can do. This is in my arsenal. My claim is I can also do a little bit more than that. What is that? I can you know what? Okay. Let me move this up instead. Okay. I can also go to alpha times RA bar, alpha times RB bar for any non-zero alpha. Pick some field element like number 2. Maybe that's a field element. I just multiply everything in here with the number 2. I will multiply everything in there with the number 2. I can do that. Why is it okay to do it? Because it's non-destructive. I can divide by 2 later on and recover the original things. Ideally, I would just make it multiply by 0, call the recursion, multiply by 0, call the recursion, and done. But if I call by 0, multiply by 0, I lost information. So somehow, I want to multiply by 0, but I cannot. So what can I do instead? I'm going to say that I need to evaluate some polynomial at the value 0. To do that, I'm going to evaluate at many other places and deduce it at the value 0. Okay? So the template now is going to be the following. Again, I'll draw a picture. We'll talk about that like a caricature. Okay. So what I'm going to do is, for alpha equals something like 1 through some numbers, some number of values, I'm going to go from, this is RA bar, RB bar, RC bar. I'm going to make them alpha times this. Okay. And this is like a straight line program too. I'm just saying multiply this thing with alpha, multiply that thing with alpha. Right? And after this, I'm going to make the recursive call to compute to offset it by the value of the left, and offset this by the value on the right. And as I said, we are going to focus only on the ith coordinate. We'll have an outer loop where we'll do this for every coordinate, somewhere a loop for every coordinate in the output. Okay. And now, after I do these two things, I will say we know this is y, this is z, right? These are fixed. Y and z are fixed in the sense that they do not change based on alpha. Okay. I'm going to replace this with f tilde I of okay. All right. So now think of this as the initial RA bar and RB are fixed. The y and z are also fixed in the sense that we're only going to focus on changing alpha. Okay. So now I can think of this as RCI plus some, polynomial, whatever that is, it doesn't matter, of alpha. So univariate polynomial of degree less than or equal to 2k. All right. And what do I really want to compute? I want to set RCI to be RCI plus P tilde of what point? What's the ideal value that we want here? If I set alpha equals 0, I get the actual thing, which is y comma z, the left and right things, right? So I want to put 0 here. That's our end goal, right? We cannot multiply it with 0, because if we multiply with 0, we lose the information stored in the registers and we cannot restore it. Okay? But we are kind of lucky in that polynomial interpolation is a good thing. Okay. So we'll talk about the exact details later on, but I want to give you the high level picture today, which is claim for interpolation. There exists coefficients C alpha, C1 up to C, let's say 2L plus 1, doesn't matter what it is. These coefficients do not depend on anything. They only depend on the field and nothing else. okay, just on whatever this number k was. So this should be k. Such that for any degree k polynomial, this holds, degree at most 2k polynomial. Okay. So the polynomial interpolation formula says that the value at 0 can be written as a sum, as a weighted combination of the evaluations at different points. And these coefficients are fixed. They don't depend on the inputs, the tree, nothing. They only depend on whatever field size you're picking. Okay. So now we kind of have a template. And so let me write that down. So I'm going to do this this is the algorithm, more or less. We'll make it simpler by choosing the points of interpolation more carefully, but I don't think that's the main point. The ingenuity is in this encoding, really. Okay. So remember, our goal is we want to compute offset u, RA bar, RB bar, RC. Okay. And yeah, so what am I going to do? For each alpha, I'm going to say offset u dot left, comma, okay. So what do these steps achieve? At the end of these steps, this register will have alpha RA bar plus fu dot left. This will have alpha RB bar plus fu dot right. Okay. The next thing you do is for I equals 1 through k, so whatever is in the current registers, I'm just going to evaluate that polynomial on those things. That's it. With the coefficient C alpha added back. So it is offsetting, right? So implicitly, what am I doing here? What I'm doing here is that this is just C alpha times P tilde of alpha. Okay, I'm computing every step of this update one after the other. I don't have to do all of these additions at time. I just need to add them one at a time. Okay, and when I finish doing this, I'll end up with exactly at the end here, I will have, okay, maybe after each thing, I do a cleanup, which is okay. So these four things are the cleanup. I think I should change this order here. So let me be careful. So this is going to be RV bar, RC bar. Okay. Right, because we're changing which one gets updated. Instead of updating the third register, we're always updating the third register, but this is updating the second one. Okay. So when I do this, I would have the first register holding this value and the second register holding this value. Okay. And I compute the polynomial, add them up, and then I undo these things. Right? I subtract out minus fu left, I subtract out minus fu right, and then I divide by alpha so that everything returns back to its original state. Okay, so this is the full code. Makes sense? At a high level at least. So we're using this polynomial interpolation to say somehow I need to evaluate the polynomial f tilde u comma I at these points y comma z. I cannot get handle on them directly, but I can get handle on alpha times something plus y, alpha times something plus z. Okay. So by evaluating it at different points of alpha, as long as I don't multiply by 0, I can find, because I can undo if I multiply by any other number. Okay. So, and then I use this polynomial interpolation formula to get the value at 0. Okay. Where? Yes, you're right. So this should be alpha here. Or maybe, you know what? Actually, let me just do it this way. I guess the first thing I do is multiply those two register with alpha and then do the updates. And then I undo this multiplication to get back, restore them to their original state. Okay. And it's a little bit confusing and clever, but it requires a little bit of it is subtle. We're using this polynomial interpolation in a magical way. And when we come back on Wednesday, right now, it's good to know that there is this interpolation, there's the C alpha and so on, but where do you get these coefficients? Do you have to compute them? It doesn't matter. If I pick these evaluation points to be the roots of unity, the interpolation coefficients are just 1. Okay. So that will give the final algorithm, and I'll talk about that on Wednesday. So the same template, but instead of evaluating it, 1 through 2k plus 1, we'll evaluate them kind of in a slightly different way so that you don't have to even compute these coefficients. The coefficients will just be 1. Okay. So in the original paper, they talk about roots of unity and how they're important and so on, but it's not that important. It's really this polynomial interpolation. But the roots of unity make the coefficients just 1. Yeah? Cook and Merz. This one came last year. And in some sense, this view is based on a note that Oded Goldreich posted a month or 2 ago. It's kind of some simplification, and you also get some improvements. And yeah, but the main idea is there in that. Okay. It's the definition of offset was the last one being changed. I think so. Did I define it? Yeah. So in offset, always the last one gets updated. Okay, we had to fix some convention and then change how you make the recursive calls. Okay. Yes. Yeah. Because there you also had this Ri times something, so that makes it trickier. Yeah. Okay. All right. Okay, I'll see you all on Wednesday.